Okay, let's get started because we all want to go, right? Um, Hello, everyone. Thank you for coming. You're the ones who are seeing NDC through to the bitter end. I applaud you, and more importantly, I thank you. I thought I was going to do this to an empty room, so I am super grateful. Um, so, my name is Dale. I'm a developer for IBM with a background in AI and machine learning. This is going to be essentially an intro to AI and machine learning talk, but hopefully with a bit of a difference. I'm going to be giving an intro to AI and machine learning talk through the eyes, through the lens, through the experiences of school children. Because I spend a lot of time doing work with local schools. I go into schools and I run computing classes, machine learning classes. I teach children aged 7 and up about what machine learning is and what it's all about. This photo actually isn't from a school because I'm not allowed to go into school and take photos of the children. They get a bit weird about that. So this is from MozFest, an event from a couple of years ago, and that's my daughter running a machine learning workshop, and I was running around being her happy helper. But what I'm going to be doing is telling you about things I've seen school children do and how they've sort of stumbled onto some really fundamental lessons about AI and machine learning. So a bit of context to get started with. This is Scratch. If you haven't seen it before, this is used around the world to teach coding to kids. The idea is programming concepts are represented as these blocks on the palette, and the kids drag them onto the canvas and they snap together, and that's how they make their programs. And this gives kids this like friendly, accessible, approachable sandbox that they can learn about coding in. So what I've been doing is putting machine learning models in Scratch by adding it to that palette. So kids can do what they used to and make their programs, but like this, these blocks represent ImageNet. Now, if you haven't used ImageNet before, it's a machine learning model that you give it an image and it tells you the object that's in that image. So they can make things like this that tell them, you know, there's a Pekingese in that photo and a baseball in that one and a brown bear in that one, with just, you know, that many blocks. Or this one, which is using a face detection model. Spot my daughter again. So a few sprites here, a nose and an eye and an eye, and each one is finding the location of something on her face. So with a tiny little bit of coding, she made this like emoji masky, facey thing. So what did they learn? What did the kids learn from doing this? It was really intentional using Scratch to do machine learning lessons. I didn't want to build a whole new tool and teach the kids a different way of doing things so they could do AI and machine learning, because what they learned from this, well, firstly, there's a pragmatic thing, right? It means I don't have to teach them how to use a new tool because they all learn Scratch in school. They all know what Scratch is. So that gives me a big head start. But more usefully, this sends a message to them that machine learning and AI isn't replacing their need to learn code. It's not me coming into the school and saying, you know, your teacher's been teaching you this Scratch code stuff. Don't worry about that because AI is coming and AI is going to magically figure it all out. Instead, what the kids learn is machine learning is adding to what they've already learned. It's a new tool in their toolbox. It's extending what they can do with code. It's not replacing it. But giving them existing machine learning models is nice, but really what I like to get the kids to do is to train their own machine learning models. So I built a whole load of tooling around getting the kids to make really simple supervised learning models. So what they do is they create these like buckets representing classes, and they fill it with training examples, and they use this to train a machine learning model. And they can do this for text and pictures and sounds and numbers and all sorts of stuff. So what they're doing here is making a chatbot. They were learning about the moon. So they came up with some ideas of what questions they thought someone might ask about the moon, like how big it is, what's it made of, what's the temperature on the moon, that sort of thing. And they filled each of those buckets with lots of examples of how they would ask that question. They then use that to train a machine learning model, and then they're back into Scratch, because when they jump into Scratch, their model is represented with these new blocks. And then they can script what answers they want their bot to give when it recognizes an answer. And then what you see there is they ask what's the temperature, and the bot answers. So what they learn from this kind of thing is the workflow of how an AI project works, a machine learning project works. The idea of predicting what commands you think the user is going to give, creating those buckets, and then collecting examples of how someone would give those commands. So filling in each of those buckets with all those examples, and then using those examples to train a machine learning model, and then scripting the responses of what they wanted it to do when the system recognized the intents. And more than that, that idea of, when it gets things wrong, go back to the training examples, add new training examples, train a new model, go back, try it out, it gets it right. That cyclical workflow of how machine learning model projects tend to go. So by doing this for themselves, even in a small scale, like a lesson or so, they start to get a feel for how AI projects go, how they work. This is a fun project. We made a Pacman game, a really simple one. So the buckets are the moves, going left, going right, going up, going down. And each one is filled with examples of where Pacman was and where the ghost was. Well, we were doing nano and monsters to, copyright. So what happened is they train a model so that the machine learning model can take control of the little Pacman character and then drive it around the game. Now, because, primary school kids, they're only like 9 or 10, so we did a really simplified version of Pacman, so only one ghost and not many walls in the way, just to keep it nice and simple. But the principle's basically the same, right? So what they had is this Pacman character that can navigate around the maze and try and avoid that. So what did they learn from this? Well, one interesting thing is you give them a little time to collect training data, and then they try it out, and their Pacman is rubbish. It just runs straight into the ghost, or it dives into a corner and gets stuck there. So then you sort of say, well, give it a bit more training, a few more training examples, train it a bit longer, then try it again. And they see it lasts a little bit longer and then gets caught. So then a bit more training, and it lasts a bit longer. And the more training they give it, the longer and longer it can evade the ghost, until the point where it actually gets perfectly able to just keep avoiding the ghost forever. So what do they learn? That correlation between the quantity of the more training data you give it, the better the accuracy tends to be. And that quantity of training data having a really major impact on the performance of the machine learning model. I really like using games with kids for this sort of stuff. So another project I've done really similar is noughts and crosses. So same sort of idea. You collect training examples of all the possible moves. In Pacman, there are 4 possible moves, go up, down, left, right. In noughts and crosses, there are 9, so there's a bit more training data. So this takes ages. So what do they do? Well, one of the classes I did this with sort of suggested, well, instead of all of us, all 30 kids, each of us training our own separate machine learning models, why don't we all work together? Why don't we all put our training examples into one project? And then we'll have hundreds of examples really, really quickly. I thought it was a great idea. So yeah, let's do it. Let's give it a try. So we set up one project and they all started putting their training examples into there. And really, really quickly, they had a machine learning model that if it didn't win every game, it would at least force a draw. So what did they learn from that? That idea of crowdsourcing for training data, a really common aspect of a lot of successful machine learning projects I've worked on in the real world is how we collect training data by trying to do it at scale with a large number of users. Or even gamification. The nice thing about the Pacman one was they didn't have to type in their training examples. They weren't typing in the coordinates. We played the game, right? You get them to play Pacman, and every time they pressed a button to control the Pacman, it was adding a training example into one of their training buckets. In fact, actually, getting them to do a lot of training data wasn't a problem. Getting them to stop collecting training data and get on with the lesson, that was a bit more of a problem. This project I did with some slightly older kids. They were doing some stuff around media literacy. They were learning about how different media outlets, different news outlets covered the same sort of stories. And the different ways different media outlets use language. So we wanted to see if we could train a computer to recognize some of those patterns. So they picked 4 national newspapers in the UK, and they got the main front page headline, the top story, the top headline from that newspaper for each day, and collected a load of examples. And then we used it to make this little game where you give it a new headline, you type in a headline, and it will try and predict which newspaper that headline probably came from, and then it puts the newspaper on the right shelf. So when we started in that, I was sort of getting them to type in a headline that they'd already used in the training. And then I sort of asked them, well, do you think that's a good test? Like, have you proven that the computer has really learnt how to make a prediction if you've already told it that headline came from that newspaper? And they were like, oh no, that doesn't really prove it. Oh, so what should we do? Well, why don't we pick new headlines that we've never shown the computer before? Then we really know if it's learning. That's a better test. And I tend to use metaphors, so I sort of ask them, when you're doing your tests at the end of term, does the teacher give you questions she's already told you the answers to, or does she give you new questions to check if you've learnt it? And then the kids go, oh, well, it's new questions that we haven't seen before, and that's how the teacher really knows if we've understood it. Well, that's what we do with computers too. That idea of needing to separate out training and test data is a lesson they tend to sort of work out for themselves. This is a fun project. You tell the kids to create 2 buckets, one for the nicest, kindest, loveliest compliments they can think of, and one for the meanest, cruelest, nastiest insults they can think of. Generally, this bucket stays empty. That bucket gets full really quick. And I've learnt some new words. This is a risky one with older kids. I've done this with teenagers, and I've learned all sorts of language. But what do they learn from this? There's often an assumption that machine learning with text is about training the computer to understand what the text means. But it's not just about meaning. It's not just about intent. You know, computers learn to spot patterns in the examples that we give it. And those patterns could be around intent, but it could be about writing style, formal or informal. It could be about emotional, happy, sad, or like this, you know, around sentiment. So that idea of being able to train a computer to recognize different kinds of patterns in groups of text. But what we do with this one is, so we train the computer to recognize a compliment or an insult. We go into Scratch, and then we get them to make a character. Normally, I'll get them to draw it themselves, because particularly the younger kids, they like being creative, but I can't draw, so I went with an emoji instead. So you type in a new message that it hasn't seen before, either something nice or something mean. If you say something nice, it changes the costume, and it looks happy. If you say something mean, you dumb moron, it cries. And then obviously, all the boys spend the rest of the lesson trying to make the face cry. But hopefully what they learn is, you know, like I said, machine learning can be used to recognize lots of different types of patterns in the examples we give it, but also about different uses of machine learning, like creating systems that can respond appropriately based on the emotional reaction of the user. Alexa or Siri or Google Home, those kinds of devices, quite often there's at least a few kids in the class who've got one of them at home, and even the ones who haven't got one at home have seen it before and are aware of it. So it's a nice thing to get the kids to create because it's a use case they're familiar with. So we create a couple of examples, you know, turn on the fan, turn on the lamp. They fill those buckets with examples of how they would give that command. And then we make a virtual Alexa, an Alexa that only knows how to do 2 things, turn on a fan and turn on a lamp. But they can phrase that command in natural language, in English. Please turn on the fan for me, and then the fan animates. And it's a nice way of giving them some insight so that Alexa isn't this magic black box in the corner of the room. They start to get some idea about how it was made, what went into it, that workflow that I was talking about before. But the nice thing with this is, because it's a use case they're familiar with, you can use this to sort of tease out interesting ideas. So one thing I've done with this is, like, you come up with a really obscure way of phrasing it, right? So you ask the thing, like for the fan, activate the spinny thing. Or something that's a bit weird, something that they haven't really trained it how to cope with that, so it's something it gets it wrong. So then it gets it wrong, like you tell it activate the spinny thing and it turns the lamp on. So you sort of say, well, what do we do now? How are we going to fix that? And you prod them a bit and they sort of go, well, what about if we go back to the training examples and add that to the bucket so that next time it learns how to get that right? Good idea, let's try it. So we go back, add it to the training buckets, we try it again and it starts getting it right. That kind of insight, I think, is lacking in the general public. Because when I see stories like this, that Amazon are getting examples of things Alexas get wrong, and people are labeling those examples and putting them into training data, as someone who's been working in machine learning for a long time, I go, well, yeah, of course they are, because that's how machine learning projects work. But apparently that's a big surprise to most of the public. So one of the nice things about doing these kinds of projects with schools is, now, by no means am I saying I tell the kids that this makes it okay. And actually, it's a really interesting conversation. Once they understand the idea and the motivation behind it, you can have that discussion of, well, do you think it's appropriate? Do you think they should be doing that? Do you think they should tell you when they do that? How should they tell you? And kids have a great sense of what's fair and what's right and what's wrong. But if they're coming from an understanding of the motivation of the tech companies who do this, they're able to have that debate in a way that I don't think the media really are. Sticking with the Alexa one, the other thing that this lets kids do is play around with confidence scores, because those of you who've done machine learning stuff before will know that machine learning models don't just give you an answer, they give you a score, like a percentage of how confident the system is that it's correctly understood your question. So here what it's doing is, the class has got it's checking the confidence, and if it's less than 50% confident, it recognized the input. It just says, I don't understand. So you can ask it things like, make me a sandwich, or what's the capital city of France, or something like that. And instead of just turning on the lamp or the fan, it will say, sorry, I don't understand. The idea of the confidence scores and the way that we use them, and again, trying to use examples with what the kids will have seen already. So like when they ask Siri something and it says, sorry, I don't understand, how did it know it didn't understand that? Like giving them some idea of what went into that is really helpful. They also start to, because the tricky bit is, how do you know that 50% is a good number? So getting the kids to experiment with that threshold. What happens if you set it really high? What if you make that 99%? Well, it says, I don't understand to everything. It never confidently turns on a fan or a lamp. It just goes, oh, I'm not sure. What if you make that number 5? Well, it never says, I don't understand. It always thinks it's got an answer and does it. And getting the kids to try and find that for themselves and to get them to describe it, I thought was really interesting. I had a fantastic, a bunch of students describe this as being like, if they set the number too high, they described that as the computer was being shy. Essentially, they thought the computer was being timid. They said it was like when they knew the right answer when the teacher asked a question, but they weren't confident enough to put their hand up because they weren't sure if they were right, which I thought was the best metaphor, like way better than anything I could have come up with, and a really nice way of sort of describing that. And it means you can have those discussions with the class about, well, there is no one number threshold that you should use. It depends on the project, because it kind of depends on how risky, like, is it okay if you get something wrong occasionally? For some sorts of projects, a high number is appropriate, for some, a low number is. And getting the kids to sort of see that for themselves, I found really interesting. But there are other ways of using confidence scores as well. I did this project with a slightly older group. So we were training it to recognize Lego figures, right? So you'd hold a Lego figure in front of the webcam and it would say, in this case, Doctor Who, right? And that one had a really high confidence because we'd only trained it to recognize like 4 or 5 different Lego figures. But I asked the class, well, what part of that picture did the computer think was really important? And they were like, oh, no, because machine learning models are a black box. Annoyingly, I'd already told them that, so they could use that against me and go, well, you told us it's a black box, we can't work it out. It's like, well, no, don't give up so quickly. But intuitively, do you think this corner down here is why it thought that's the Doctor? And they were like, oh, no, of course not. Well, are you sure? Can we prove that? So we had a bit of an experiment. We played around with covering up different chunks of the picture, and we looked at what that did to the confidence score. So when we covered up the top left, confidence score hardly changed at all. When we covered up his foot, the confidence dropped to 56%. That really surprised me. I was not expecting his left foot to have such a major impact. When we covered up his chest, like with the jumper and stuff, I thought that would have a major impact. It dropped the percentage, like confidence, by about 20%. So we wrote a little thing in Scratch, and like I say, it's fantastic. The kids know Scratch, so they know how to do this stuff. We did it so that it moved the box. It tried every different position of the box, and then we made a visualization by changing the transparency of the box based on the difference it made to the confidence. And it made that. So suddenly, at the start of the lesson, I was like, do you know what part of the picture made the computer think this was Doctor Who? And they were like, you can't tell. Well, you can sort of tell. And this is done by primary school kids, which I think is fantastic. Different ways of dealing with that challenge of a black box and how we can try to infer what the computer is thinking. It's a lesson that I think there are some adult developers could do with learning. I do engineer some things that I know I want the kids to learn at the start of the lesson. So I do try to trick them into stumbling into some things. It's always more fun if I don't do that, but sometimes like this, you can probably tell where I'm going with this. We trained it to recognize apples or tomatoes. And we collected a load of photos of apples and a load of photos of tomatoes. Can anyone tell where I'm going with this? Yeah. Exactly. They didn't see it coming. So we showed it, like you say, a red apple, and unsurprisingly, it stuck most of the red apples in with the tomatoes. And similarly found really unripe green tomatoes, and it put them in with the apples. But once the kids see that happen, initially they're surprised. They're like, oh, hang on, what? But then you ask them, well, why do you think it's done that? And of course, they all immediately spot it. So you ask them, well, how do we fix this? And they're like, well, maybe if we go and find some photos of red apples and green tomatoes, add that to the training, then we try it, and yes, it gets it all right. There was one time when this happened that it wasn't engineered by me, which was much better. I was getting them to make like an AI sheepdog. So this idea that it would learn to recognize cow or sheep, and then we made this game in Scratch that would move the animals to the right part of the field. Because I thought that'd be kind of cute, because I thought like AI sheepdog would be fun. But what I hadn't thought is there was a couple of kids that had done like this, photos for all their training examples. And then when they were doing the test for the sheepdog bit, they had loads of cartoon images of cows and sheep, and it was getting most of them wrong, putting them in the wrong place. But it ended up being a great learning opportunity for the class, because I could sort of say, well, why do you think it's getting them wrong? It was like, oh, well, we never taught it how to recognize cartoons. We only taught it how to recognize photos. How do we fix that? Let's get a load of cartoons and stick it in the training examples and then try it, and it works. So that idea of what happens when you test with things that weren't represented in the training, what happens if you try to get the machine learning model to do something that you haven't taught it how to do before, haven't trained it how to do before, and how it typically ends up getting a lot of things wrong. It's been really interesting to see the kids learn that for themselves. Slight variation on that. I've done this project loads of times. Rock, paper, scissors. Get the kids to hold their hand up to the webcam in the shape of a rock or paper or scissors. Once they've trained it to recognize their hand, we make a game in Scratch where they play rock, paper, scissors against the computer. And it's kind of fun. Like I said, games work well, keeps the kids motivated. One of the times I did this lesson, there was one kid who did a really good job with rock and scissors. He had he did a really good job of varying his training examples, because there's always some keen kids who hold their hand still and hammer the take photo button and end up with 10 virtually identical photos, and their models are rubbish because there's no variation. But this kid had done a good job. Rock and scissors were good. But when he was taking photos of paper, his mate had come around and stood next to him, and his mate was in the shot of the webcam. So in all of his paper photos, it was a hand and a person. In all of his rock and scissors photos, it was a picture of a hand. And he didn't notice that. It wasn't intentional. He didn't pick up on it. And then when he was testing it, when he'd made his game, anytime me or the teacher came and stood next to him, the computer thought he was doing paper. And it was like, it took us so long to figure that out. It was like 10 minutes of scratching our heads, and why is it doing that? And when the penny finally dropped, it was literally, he would hold his hand up and the computer would think rock, and then I would jump in and it would go paper, and then I would go away and it would go rock again. And I loved that. Like I say, it's so much better when I don't engineer these lessons, because what they learned was machine learning systems learn from patterns in the data we give it. Those patterns might not be the patterns you'd intended it to learn from. It might not be what you'd initially set out for it to learn, but they will learn from examples in the data you give it. And this is something that we make in that kind of mistake we make in the real world all the time. This project we did was around making recommendations for places people might want to go on holiday. So we came up with a few buckets of museum and fun fair and theme park and a fishing pond, filled it with examples of what people would describe as their hobbies and interests, and then we made this little phone app that you would sort of say, I would like to relax, and it would go try going fishing. So they make this, and it works really nicely, and you have a bit of a discussion about how machine learning is commonly used in recommendation engines. It's how Spotify can recommend what you might want to listen to, how YouTube recommends what you might want to watch next, how Amazon recommends what you might want to buy. What I liked with this project, what I've done with some of the older kids, is get them to go back and add. So we've already got a fun fair, add a theme park. So you've got two kind of similar things. And then get them so that the fun fair bucket has like 2 or 3 examples in it. And get them to put 40 examples in the theme park bucket. So it's really unbalanced. And then when they start asking their app, I want to do something exciting, theme park. I want an adrenaline rush, theme park. I want to go on rides, theme park. It never says fun fair. And then you ask them, well, why is it never answering with fun fair? And they visually see in the training buckets that, they've got loads of examples in one bucket and hardly any in the other. And normally with a bit of nudging and a bit of prompting, they go, oh, well, I've told it the right answer is funfair. Like, I've hardly ever told it the right answer is funfair, but I've told it the right answer is theme park loads of times. So the computer's learned that the right answer is normally theme park. That's a really, like, that's a penny dropping moment. That's because often the kids come into the class with this assumption that the good algorithms, the smart code, the smart algorithms give the right answers, and the rubbish algorithms and the rubbish technology gives the wrong answers. The whole idea that actually these systems are influenced not just by the quality of the code and the algorithms, but by who's trained it and what they use to train it with, that really surprises them. Most of them never see that coming. That idea that just by the person who's choosing the examples they feed the model with has that level of influence over what answers the system gives, that really surprises them. And I think to a non-technical, non-developer person, that isn't initially intuitive. So then you ask them, well, what do you think about that? Is that okay? You happy with that? And it's an app telling you where you can go on holiday. So they're like, yeah. You go, well, what if the reason why the funfair bucket is hardly empty, is mostly empty, and the theme park bucket is really full? What if that was because the owner of the theme park gave you a big sack of cash to put loads of examples in there? Is that okay? At that point, some of them will come off the fence. They're like, okay, that doesn't seem fair. But most of them are still, it's a holiday app, who cares? So then you go, well, okay, what if this wasn't recommending places to go on holiday? What if this was recommending the best medicine for you? And the buckets were drugs from different drug companies. And the reason why you put loads of examples of medical records in one bucket and not many in the other is because the manufacturer of that drug gave you a sack of cash. At that point, they're all off the fence. They're all, oh, hang on, would that happen? Is that how that works? And you're having a debate about transparency in AI with a bunch of 10-year-olds. And that need for transparency in the way these critical systems, these systems that have a massive impact on our lives. And, you know, how do we know what went into training these systems and who influenced what went into training these systems and how these systems are being used? By doing this for themselves, by being able to bias a machine learning model for themselves and seeing how easy it is to do it and the way that the technology behaves. Like I say, kids have a fantastic sense of fairness and justice and right and wrong, and you can have really interesting debates with them about that after they've sort of had a little bit of exposure to what's possible. I like doing projects based around sound, so if it makes for a really noisy lesson, but you can get them to do little sound recordings. So with this one, like I got the kids to invent new words because the machine learning model already recognizes words in the English dictionary. So I get them to come up with like secret code words, secret code noises for a few different places in town. And then they make a game where when they say the code word, the spy goes to the secret place. So it's kind of fun. But what's interesting is when we make something like this. So this is a game where when she shouts out laser eyes, it finds where her face is using that face detection model I mentioned earlier, and it fires lasers out of her eyes, and she has to smash the bottles. This is a fun one because you end up with a room full of kids screaming laser eyes. But what I like about this and what they learn from this is this idea that typically it's not just about one machine learning model for one project. What we do is we assemble a collection of machine learning models that all do different kinds of things into a solution. So this one is using the face detection model I talked about a while ago, which is sort of just off the bottom there, and the sound recognition one where she created a bucket and filled it with sound recordings of her shouting laser eyes. But that idea of how we combine multiple models to do a single job, often, again, they don't initially realize. They just assume that an app is going to use a model to do one thing, and that's the app's job. This is another one that I engineered. So I got half the class to train a model to recognize different types of fruit. I got the other half of the class to train a model to recognize different types of animal. Didn't tell them why, just you're making a model to recognize fruit, you're making a model to recognize fish, insects, or birds. And then we made this out of it, where we gave it Rorschach pictures. And we used both models, this half of the classes and this half of the classes, at once. And one half of the class, given the same picture, their model said it's a plum, God knows why, and their one said it's a bird. That one sort of makes sense to me. And we tried it with loads of Rorschach pictures. That one it thought was a banana, same picture. The other model thought it was a fish. So you ask them, well, why is it doing that? I mean, that isn't a banana, that isn't a fish. Why is your model doing that? And they would go, well, yeah, but we didn't teach it what that was. And you say, well, why do these two machine learning models, it's the same technology, why are they giving different answers? It's like, well, that one was only taught to recognize these things, and that one was only taught to recognize those things. There's a reason why I was making the class do that, is because I'd just seen this in the news. Did anyone see this project? It's a couple of years old now. For those who haven't seen it before, it was a project where they trained a machine learning model using scenes from horror films. Loads and loads of scenes from horror films. And what this does is you give it a picture and it classifies it as something from a horror film. So it would do stuff like this. They would give it Rorschach pictures and it would go, this looks like a man being shot dead. And the news were getting terrified about how this AI is a psychopath. And why have we disturbed this poor technology? They force-fed, literally they force-fed this AI a stream of macabre images from horror films, and they've made it into a psychopath. Comes back to what I was saying before, that give the kids a little context and it gives them an idea about how, it helps them to recognize when the media is portraying AI in certain ways. It helps them to understand what's going on under the covers. Because ultimately what we're talking about is what happens when you ask a machine learning model to do something it wasn't trained to do. Norman was trained to recognize scenes from horror films. So if you show it a Rorschach picture, all it's going to be able to do is give you an answer that it's been taught how to give, something from a horror film. This one was a fun one. One of the ways we can collect the training examples is by drawing directly onto an on-screen canvas. So I got them to write examples of postcodes, of zip codes, onto the canvas for a few local towns near us. So a load of examples of Oxford, Guildford, and Southampton. And then we made a postman pack game in Scratch, something where you would write onto an on-screen envelope, and it would recognize what they'd written, and then send that envelope to the right van. So like for this one, you could write the code for Oxford, scribble that on, they click on the cat stamp, their machine learning model that they trained would recognize what they've written, and the letter goes to the right place. Now, partly this is just a nice little tech demo, right? It's a fun little thing. It's teaching them about handwriting recognition, optical character recognition. It's a fun project. But what I liked about it was that it gave me that chance to talk to them about how this is how, it's a simplified version, a cut down version, but it's a version of how sorting offices have automated the sorting of envelopes and packages and stuff. And that idea that AI is everywhere, invisible AI, it's not just the systems that they do notice like Alexa and Siri. The fact that all of our days are impacted in 101 tiny ways that we don't even notice by these AI systems. Projects like this I like because it helps open the kids' eyes up to, it helps them to spot where these places where AI and machine learning is being used. My last fun one, we did a project with books. So we picked a few different genres of books and we trained a machine learning model to recognize what a music book looks like, what a cookery book looks like, what a kid's book looks like. Each of the kids picked different genres, but those are the ones that I picked for this video. And then we made an app that would, you show it a new book that it hasn't seen before, and it would tell you which shelf in the library that book should go onto. And the main reason I like that is just because it meant that we could teach the kids that, yes, a computer can learn to judge a book by its cover. And that one pun is literally the only reason I did this project, but it made me laugh. So, I've told you about loads of stories of, I've been doing these kinds of lessons with schools for years now. And I'm continually impressed with how, with just the tiniest bit of nudging and prompting, even really young kids can intuitively understand some fundamental lessons about how we apply machine learning and AI in the real world. This is way too many for you to remember, so let me sum it up as this. The idea of how we phase a machine learning project. Try and predict what you want it to be able to do, collect examples of that thing being done, test to make sure it understands examples of that, identify examples of where it's getting things wrong, go back, add that to the training, test it again, keep going around that cycle till you're happy. The need to keep your test data separate, how you can understand what the machine learning model is telling you, that, the role of confidence scores and so on. The impact of bias, whether that's accidental bias because you're giving it test data that isn't similar to anything you've trained it with, or where you're intentionally skewing it, and what kids think about that and what they think is fair and right about that. The role of AI, whether it's those invisible apps that they don't even notice is there, the way we assemble solutions out of multiple machine learning models. All of these are things that that I've seen kids learn for themselves with just a tiny bit of prompting. And as I said, a bunch of lessons in there that I think there are people doing this professionally that wouldn't hurt being reminded. And with that, thank you very much for listening. I hope that was interesting. And thank you for staying to the end of NDC. If anyone has questions, I'm here for a bit, but otherwise, safe travels home.